force in space. So if the force is directed from the origin to any point, let's say x, y, and z, then we imagine that this is the main diagonal of the box with dimensions x, y, and z. So remember, the force is directed from the origin to this point here. So the angle that this force or this diagonal D makes with the coordinate axis would be theta x, theta y, and theta z respectively. So take note that the components of force are the following: Fx, Fy, and Fz. Then this Fx and the force F will form a right triangle with F as the hypotenuse and the 90-degree at the intersection between this diagonal and the x-axis. So from the figure, also the Fy makes an angle of 90 degrees with this diagonal on the top, and it's 90 degrees between the diagonal and the y-axis. And we conclude that this Fz here and F, their tips are connected with an imaginary line which is perpendicular to Fz, so it's 90 degrees between this diagonal tip to tip and the z-axis. So from the figure, cosine of theta x is in terms of the components of force, it is equal to fx over f, and cosine theta x in terms of components of distance is x over d. Cosine theta x is also x. This is x over d, or the distance or diagonal. Equating the cosine theta x, we have fx over f equals x over d, or rearranging fx over x equals f over d, or the ratio of the x component of force to the x component of distance is equal to the force divided by the length or the distance where the force is directed. Likewise, cosine theta y equals fy over f. Cosine theta y is also y over d, and equating cosine theta y, fy over f equals y over d, and then rearranging, we have fy over y equals f over d. So the ratio is the same or equal. Lastly, cosine theta z is equal to fz over f equals also cosine theta z equals z over d, equating the ratio. So fz over f equals z over d. So rearranging fz over z equals f over d. So fx over x equals fy over y equals fz over z equals f over d, and this ratio f over d is called the force multiplier. So this is the constant or equal ratio. So it's easy to remember because we have x component of force as to x component of distance equals y component of force equals y component of distance, z component of force over z component of distance equals force over distance. Then also fx squared plus fy squared plus fz squared, the sum of the squares of the components is equal to the force, the square of the force. Dividing everything by fx squared, then we have fx over dividing everything by f squared, we have fx over f quantity squared plus fy over f quantity squared plus fz over f quantity squared equals f over f quantity squared. This ratio is 1 at the right, in the right side, and fx over f is cosine of theta x, fy over y is cosine theta y, fz over z over f is cosine theta z. So the sum of the squares of the direction cosines is equal to 1. So always remember this. Cosine squared theta x plus cosine squared theta y plus cosine squared theta z equals 1. And when theta x equals theta y equals theta z, or when this box is a cube, then the angle theta would be equal to 54.74. And that is, you just add these 3 cosine squared theta equals 1, then you can solve theta 54.74 degrees. Then let's have the general proof of the Varignon's theorem. So that's the resultant force, and this resultant has, let us say, in general, three components, namely P, Q, and S. Then the moment of the force about point A is simply the position vector RBA cross the force R. That's the application of the moment of cross product, rather, moment of a force about a point. So moment of the resultant about A is equal to the moment sums of these components. So we have RAB cross P plus RAB cross Q plus RAB cross S. Factoring out RAB, then we have quantity RAB cross quantity P plus Q plus S. And take note that the sum of these forces or these components is simply the concurrent forces is simply this single resultant force R, which also acts at point B. So this is the resultant. So that's the formal way of proving the Varignon's theorem. So the moment of the resultant is equal to the sum of the moments of its components, or the Varignon's theorem. Then let's have the principle of moments. So we have the force here, then the force is, let us say, directed from point A to point B. So A and B are points on the line of action of the force. Then we have a moment center O, or any point. Then we have the position vector from O to A and position vector from O to B. Then in general, we have position vector R from O to any point on the line of action of the force. Then moment of the force about O is simply the cross product of the position vector R with F. So R cross F is the moment of F about the point O. So if this is the extension of R, and then R and F forms an angle of theta, and this other angle is 180 degrees minus theta. So this is the moment of the force, that's the sense. So the moment of the force about point O is another vector perpendicular to the planes of the force, or the planes of ROA and ROB, which is the same plane as the force, and it is also equal to this sense of moment. So that's the moment of the force about point O, R cross F. Same is true with this sense or magnitude of moment. Then by cross product, we define this as moment of F about O as R cross F equals R times magnitude of F times sine of theta. Now, the theta doesn't matter if it is theta or 180 degrees minus theta, because from trigonometry, supplementary angles are, sine of supplementary angles are the same. So remember that sine of theta and sine of 180 degrees minus theta are the same. Then in this figure here, if we denote R as the hypotenuse, as magnitude, then opposite of R is the perpendicular distance of F from O, and therefore, because this angle is also theta, therefore this perpendicular distance D is R times sine of theta. So D is R sine theta. So R cross F by definition is magnitude of R, magnitude of F times sine of theta. Rearranging, R cross F equals F times R sine theta. And take note that R cross F is the moment of the force about point O in vector form. And this is the direction of that, or the sense of that moment about O. And we interpret R sine theta as D, the perpendicular distance of the force from the point O. And that's why F times D is the moment in scalar form. So we now interpret that R cross F is really the moment of the force about point O. And remember that the position vector should be from the moment center O to any point on the line of action of the force. So therefore, moment of force about O is also ROA cross F. It is also ROB cross F. So moment of a force in space. So let's consider a force acting at the point XYZ in space. And before we compute the moment of this force, let's resolve it into components so that we can apply Varigton's theorem. But before this, we have to discuss this situation here. Then when you open the door, and these are the lines of the hinges, there are three components of the force that must be applied to the doorknob. So we have a force which is parallel to the axis of the hinge. We have the force which is on the same plane as the door, and this force, if extended, passes through the axis of the hinge. Therefore, this has no rotational tendency, or its moment arm is zero. Then by experience, if you apply a force parallel to the axis of the hinge, you notice that this door will not rotate about the hinge. So therefore, the only force that will have rotational capacity or capability is the force that is perpendicular to the plane of the door. So therefore, only the force that is perpendicular to the plane of the door will have the tendency to open the door or to rotate the door. So therefore, this component of force will only have the moment about the axis of the hinge. So therefore, by this definition, moment about OX by scalar approach and using right thumb rule, so this is the positive sense, is equal to Fz is positive because it is the same sense as this, times y, then Fy is negative, so minus Fy times moment arm Z. MOY, on the other hand, is equal to, this is the positive sense of moment about y, that one. So it is equal to Fx, you look at Fx, it has the same sense, times Z, then minus Fz times moment arm X. Take note, Fy is not included because Fy is parallel to the y-axis, so remember that principle here. And finally, moment about OZ, the positive sense would be in that direction. You position the right thumb towards the positive z-axis, and it is equal to Fy. Fy is positive times x, then minus Fx times y. So that's it. Do not memorize the moment of the force in terms of its components by memorizing these formulas, but rather you have to apply right thumb rule. Now, if the force is directed from point A to point B, wherein the terminal end is B, then delta x, or the dimensions of the box, would be xb minus xa, yb minus ya, and z sub b minus z sub a respectively. So the distance AB therefore equals square root of xb minus xa quantity square plus quantity yb minus ya quantity square plus quantity z sub a minus z sub a quantity square, z sub b minus z sub a quantity square. And cosine theta x would then be fx over f, or xb minus xa over distance AB. Cosine theta y would be fy over f, or yb minus ya over distance AB. And cosine theta z would be fz over f, which is fz over f, the original definition, and with respect to distance, we have z sub b minus z sub a over delta over distance AB. So remember that these cosines of theta x, cosine theta y, cosine theta z are called direction cosines, while the corresponding angles are called direction angles. And remember that the sum of the squares of these direction cosines is unity, or 1. So moment of a force in space above a point. So we already defined this as equal to position vector r from the moment center to any point on the line of action, cross the force. So in this case, RAB cross F, and the moment is a vector and it is perpendicular to the plane of the force. So that's the sense. And what if we have to compute the moment of a force about this axis, which is not perpendicular to the plane of the force and in general is inclined? Then, having found this vector, and if we express the axis as a vector, as a unit vector of the axis, then we can compute the component of MA, or the moment of the force about A, along this, or we can project MA along the axis. And because we have formed a right triangle, and if the angle between this moment vector and the axis vector as beta, then that component is simply MA times cosine of beta. So in other words, moment about the axis represented by this, which is a scalar, is equal to MA times cosine theta. So component of MA cosine theta, that's the moment of the force about an axis, and it is a scalar. So if this is MA RAB cross F, then moment of the force about an axis, which is a scalar, is equal to MA or RAB, magnitude of RAB cross F times the cosine of beta. So that's it. So moment of a force in space about an axis is equal to magnitude of MA cosine beta, and since MA is RAB cross F, or position vector cross F, so that we can define this moment about an axis. So applying the dot product, we have MA, vector MA, that the axis vector, then it is equal to magnitude of MA, magnitude of the axis, times cosine of beta. Since MA cosine of beta is interpreted as moment of the force about this inclined axis here, so MA cosine beta, or moment of the force about the inclined axis, is simply MA that R axis divided by magnitude of the position vector for this axis here, or R axis. Since the ratio of axis vector to its magnitude is unit vector of the axis, so moment of the force about the axis, which is MA cosine beta, this one is moment of force about axis, is MA is RAB cross F, then that the unit vector of the axis. So where unit vector of axis is defined by this vector. So to understand the principle, so let's discuss some special rules in order to facilitate the analysis of space truss. So the first rule is any three concurrent non-coplanar forces will be in equilibrium if and only if all the three forces are zeros. So remember in 2D, if there are only two forces that are not collinear, then the two forces to be in equilibrium must be zero. If it is 3D, then it extended to 3. So the proof is you can orient the three concurrent non-coplanar forces in such a way that two of them will be coplanar. So in this case, N is the axis perpendicular to the planes of F2 and F3. Therefore, F1, if F1 is 0, summation forces normal equals 0. F1 has component in the direction of the normal axis, then equals 0 because F2 and F3 have no components in the normal axis. Then F1 is 0. If F1 is 0, there will be two forces left, F2 and F3. So it's just like two meeting forces at a point which are not collinear. Then from the principle in 2D truss, these forces will also be 0. So F1 equals 0, then it follows that F2 and F3 will also be 0. Then if all but one of the forces meeting at a joint are coplanar and in equilibrium, the force not on the plane is zero. So this is same as this. We'll just extend the coplanar forces to three forces or more. So F2, F3, and F4 are on the same plane, this plane here. F1 is not on the plane. So if we sum up forces perpendicular to the plane, we conclude that F1 is zero. So that's it. Only F1 that is not on the plane will be zero. F2, F3, and F4 shall be found. And they are not equal to zero. Then special rule number 3, if all but two of the forces meeting at a joint are zero, then the two forces will also be zero unless they are collinear. So it means that if it is known that F1 is zero, F2 is zero, then from four forces, they are reduced to just two forces. So remember the principle in 2D system that if there are only two forces acting at a point, then each of them is zero. So if F1 is zero, F2 is zero, remove them, there will be two forces left. Automatic F3 is zero and F4 is zero. Unless they are collinear, like in this situation here. So if F1 is zero, F2 is zero, then F3 and F4 are collinear. They are not equal to zero. In fact, they are equal. So F3 is not equal to zero. F4 is also not equal to zero. And F3 equals F4 because they are collinear. So these are the important rules and must be observed or remembered so that we can easily analyze space truss.